So we are going through the Volcano practical now, and the idea is to give you an idea how we interpret the surface deformation that we see in volcanoes. So for that, we have to go to the binder again. So for the people online, we include, I can do it, I can't say. We will share with you the link. Yeah. So the link is in the Q&A. And it's a link to the binder. And for the people in the room, you can enter through the GitHub, Comet Workshop GitHub, and the first link that you will see, and then you choose Volcano Practical. It's okay for the people? Yeah. Yeah. So we are in Volcano Practical, and the first link here is the one that you have to open. And we are on the binder. So it's similar to yesterday. To activate the cell, you have to put the shift enter. So and then back, shift and enter. So here, as I said, the idea is to try to interpret what deformation in volcanoes means. And normally, this deformation can be produced by different processes. You have seen in other practicals how movements of faults, of earthquake affect the deformation at the surface. Here in volcanoes is the same. You can have fault movement, but also you can have input of magma in a reservoir at depth. So we are focusing on that. And in general, as we have a deformation, as you have been exploring some volcanoes, we have deformations sometimes that they look like kind of circular or ellipsoidal, and that gives us an idea about the geometry of the reservoir at depth. We can also have an idea of the location of this reservoir, and also, it is very important how much volume of new material is arriving to a reservoir at depth. So basically, in this reservoir, you will have an increase in volume, an increase in pressure, and then it's this pressure that will provoke the deformation around, and we will measure at the surface. So this is important because all these uplift or subsidence that you see at the surface give us an idea of what is happening underneath. So therefore, it's important for monitoring volcanoes and can give us an alert, for example, before an eruption occurs, because it's a way of measuring, well, something is happening in these volcanoes. So here we will focus on the most simple classical model. It has been used in a lot of volcanoes. So it's the MOGI model. It's from MOGI in 1958. So it's a mathematical model in which we assume, Susie told you a bit, it's a source, a point source. We assume at certain depth. And then here we have certain assumptions. So This source is located in an isotropic medium, as it means like the deformation is the same for all the axes. It's a half space, and we have a free surface, so it means we have no stress at the top, so the surface can deform as it wants related to this source. And also the magma inside this reservoir is incompressible. So then the main source of deformation here will be the pressure, the change in volume that we will have in this source at depth. So here is the mathematical equations. We can retrieve a displacement in the x, y, and vertical displacement at the surface. And these ones will be triggered by this source that it has certain radius, certain overpressure, and also it depends on the properties of the host rock surrounding that we can have it related to the Poisson ratio or the shear modulus. And also it will depend how far away are you from the point you are measuring related to the source at depth. So it depends on your coordinates x, y, and how deep is your source. And then, well, this formula, it can be written in terms of pressure, but also it can be written in terms of volume change. And well, here is the formula related to volume change, and here you can see it's a point source. We don't care about how big is the reservoir, and sorry. So then we will see an example of a MOGI source. So basically here it is defined what is the depth of this source, how much volume change we have. Then we create a grid where we will measure the displacement at the surface in x and y, and then we assume certain Poisson ratio that here we assume 0.25, that is the typical that you can expect in the rocks. And then here we are reading a function that is basically associated to this equation. So we put what are the points that we want to measure, where is the source, how much volume change we are reproducing, and how much Poisson ratio we have. And then with this, if we plot the surface displacement, you can see in here, we can have the surface displacement decomposed in x, y, and z. For example, here in the vertical displacement, basically, we are making a reservoir at depth certain volume change positive, so we are pressurizing the source at depth, so therefore we will have an inflation all around in the host rock, and therefore in the surface we will see an uplift. And this is what you see here, an uplift in the order of 25 centimeters. And let's see how it looks in 3D. Here is the same plot, but the colors, they said again, that related to the vertical displacement of 25 centimeters. We know that the source is here, is centered at 0, 0, and is reproducing this pattern of displacement. And the arrows here, it show the deformation in the horizontal components. So as it's expanding, we are having this displacement, radial displacement all around the source. Then if we create a profile, how it looks, this deformation, if we make a profile in the y-axis, here is at y0, I think. We can see then the displacement, how it's going from 0 here and is increasing until 250 at the coordinate 0 in y. and then decreasing. So it's allow us to, this profile, it allow us to check where should be the center of this source. Same with the horizontal displacement in X. You see here, if we assume X is positive to the east, so we have a negative displacement here, and when, as soon as we are arriving to the source, it's arriving to 0, and then it's becoming positive, and it's exactly the same that you are seeing here. It's going negative and then turning to positive. So here, this displacement that you observe in Volcano, it could be 25 centimeters, 5 centimeters, or whatever. It will depend of where is the depth of your source, how much material is coming to the reservoir, etc. So here you can play with the, for example, if we put, you can change, well, if we see here, we were having, 25 centimeters, and you see like the displacement here in the y-axis, the deformation was in the order of 10 kilometers in the horizontal. And if we change, for example, to, if the source is deeper, we will have obviously less displacement. And so here, well, if you want to play later, you have to change the color bar maximum and minimum, but it's just to show you we will have less displacement in the order of 50 centimeters. And so therefore, despite this less magnitude of displacement, for example, in the vertical axis, you will see that the formation, as it's deeper, it becomes broader. So it's here is like the deformation will cover like 20 kilometers instead of the 10 kilometers that we see before. So it's a way to see how, well, if we change maybe the color bar here to, we said the maximum it was kind of 50. I will change it here just to give you a better idea. So you can see like the deformation, despite this lower in magnitude, it can cover an area, bigger area. So also looking this deformation, we can have an idea of how deep is the reservoir, where it's located, where is the center, etc. And I will leave like the original one. So you can take a look to that and see how changing these different parameters affect the deformation that we observe. And also, as Susie mentioned, depending of the line of sight of the satellite, this deformation will look different. So as you know, we can take the image from an ascending orbit or a descending orbit, and it has different look angles. So the deformation will be shifted, and it will not look like exactly in the same place that it should be. So here there is an example. You can take a look depending on the heading and incidence angles that at the end it allows you to recreate ascending or descending orbit. You can see how the deformation pattern it changed. So basically here in this exercise, we take the displacement in the X, Y, and vertical axis, and we convert to the line of sight. So like that, you can see to the line of sight, the displacement in the X-axis, the Y-axis, and the vertical axis, they are look related to the to the angle of the acquisition, and here you see this is the total displacement in the line of sight. And if you see with the related to the vertical displacement, it's different. It's a bit shifted to the right. And here you can play, this is for descending, we are using a heading angle of -10, but you can recreate, for example, for an ascending view. So you will see in this case, the displacement, it looks like shifted to the left. So then the change is more clear when you see in phase instead of the magnitude of displacement. So here is very clear, like it doesn't look like the typical deformation that you will expect in the coordinates, the geographical coordinates without this angle. So so here you can, again, I will come back to the sending, and you see here it was the ascending, and now I'm changing to the descending. And here you see it's in the opposite side. So it's just to give you an idea of how the deformation can change depending on the angle that we are looking the source. And here you can see this is the same profile that we see before for the vertical displacement in the x-axis, and then we see how this line of sight displacement is shifted a bit. And as we don't have like the north-south component of the displacement cannot be captured well due to the orbit of the satellite, at the end, this line of sight displacement is the contribution of the vertical and the east-west deformation that here is in the x-axis. So you can see that the line of sight of deformation is a bit of a combination of these two components. Yeah, so you can play a bit with this, for example. And another thing is here, when we grab this deformation, here we are assuming that the wavelength is for one fringe, it means 10 millimeters of deformation. So here we're saying it was like 250 millimeters, so you have a lot of fringes. But well, then you can change it. For example, when we were having the source at 7 kilometers, we were having just 50 centimeters. So then, if we take a look to the graph, if we have 50, yeah, you will see if it's, as here is one fringe is 10 millimeters, and the deformation in this case, it was 50 millimeters, you will see that we will have less fringes. So this is important also because sometimes you will use different satellites with different wavelengths, and you will have a different deformation in the face. So then we have the impact of topography in the surface deformation. So as I said, normally, well, MOGI is one of a lot of different analytical models that you can have. There are other models in which you can have, instead of a spherical, you can have an oblate or ellipsoidal reservoir at depth that will produce a more ellipsoidal elliptical deformation at the surface. But here, in all these analytical models, as I said, we assume that there is a half space with a free surface. So we are not taking into account how much topography the volcano has. And what is the important part of the topography is, for example, if we are assuming that there is a volcano, I don't know, with 3 kilometers of topography, and we take like a MOGI model in which we don't account topography, we will assume that the reservoir, I don't know, is at 3 kilometers depth, and you will have certain deformation. But if you account the topography, you have 3 kilometers more, so probably the deformation will be a lot less. So when you don't account the topography, you are overestimating the deformation. So we know that with 3 kilometers, we have like, I don't know, 25 centimeters of deformation. But if we account the topography, probably the source, the reservoir is 3 kilometers higher. So it's more shallow. And it's important in terms of risk at the end. If your source is more close to the surface, can be more it can be more important in terms of monitoring a volcano. So here there is a correction that has been done by Williams and Watch in 1998, in which we can take a MOGI model and they provide a correction in which you can artificially change the depth of this source in order to take into account the topography, and therefore you can reproduce a deformation pattern that is not associated to a flat surface. So here you can see an example. So if we take into account a topography here in a volcano in which it has 2 kilometers of topography, the maximum here. This is the original MOGI with a flat surface. And you see here that the topography corrected one, it will look different. So we will have variations spatially. And the magnitude of the deformation also will change. So if we take a profile again, similar profile as before, here you see the elevation of a volcano. This was the original deformation. And here, if we apply the topography, you will see that the deformation will be higher. So it can create a difference of certain times, like in this case, it could be the double of deformation. So now, well, Susie was showing to you the Comet Volcano portal, and here we will work with the Novoa volcano. So here in the Volcano portal, as Susie said, you can extract different data from each volcano, as the coherence, the displacement, the topography, etc. And this is just an example. So here for Domuyo, we can extract the Excel file with all the information, so we can have an idea about what is the coherence. So here is the opposite as Susie showed. When it's white, it's low coherence, and in black is high coherence. So you can see how the coherence affects the observation that we have. If we have snow, if we have vegetation, we will have very low coherence. So then we will not see deformation in that pixels. Also, we can have an idea of the topography of the volcano, and here we are seeing the deformation at the Muyo in an ascending view or a descending track. And then, so here we can do similar to I showed to you before. We can take a profile from here to here, for example, and see how the deformation is changing all along this profile. And here from the portal, you have the coordinates in degrees. So we are seeing the deformation in degrees, but in a MOGI model, you work in meters in a different coordinate system. So then normally what we do from the Laplon, from the degrees of latitude and longitude, we project to the UTM, and like that we have everything in meters. So here is the same that we saw before, ascending and descending, but in UTM geographic system. And then so with that done, the idea here is that you can play a bit and try to reproduce the observations that we have in ascending and descending, changing the different parameters of the MOGI model. So basically here you can change the volume change, the depth of your source, where is located the source, like here is showing in the red point. So if you move it, like the idea is like you try to fit as much as possible the observation. And here you will see the idea is to reduce the residual, that is the observation minus the model. So you can play a bit with that now. Yes, so if we have a doubt or if you want to play a bit how the formation change. You have some doubts. Yeah, that is. So this is just an example of an analytical model, and I don't know if, well, I guess you have been trying different depth, different volume change, and different location of your source. It was these three parameters that you should change. Ozone ratio, almost all the time we use 0.25. And then, well, they were asking me, Sijuan was asking me about the topography effects. Normally with analytical models, we always assume a half space with a free surface, a flat surface. But if you want to consider topographic effects, normally we can use finite element models, boundary element models, and like that you take into account the distance between the source and the surface, accounting the topography. So for the case of MOGI, this model presented here is very useful, but if you change your geometry, you have to use another method of modeling. And well, as I said before, this is just an example. It's just to give you an idea how it looks, the deformation from a spherical source or a point source at depth. But obviously, if you can have other sources, like for example, a dike or a seal that is more like a crack that is filled with magma, and then you will reproduce displacement spatial pattern different to the MOGI. Or if you have, I don't know, a reservoir more ellipsoidal, you will have something more like this, similar to a seal. Or there is other model like crack, that there are flat areas, like regions filled with magma. So, yeah, that is everything. If you have any doubts, you can ask me. And you can play around also with the line of sight or with the profile. As Susie mentioned in the Volcano portal, you can do your own profile, so it gives you an idea of where the source is, etc. So Any doubts? All good? Sí. Yeah. Okay. Okay. Sí. Yeah. You have to try, like, your residual should be almost zero. It should be almost everything clean. I know you have we never have 0, 0, 0, 0 because for the Muyo, the best source is more elliptical one. So here we are trying the spherical one. So always you will have like a bit of residuals in the border. But it's okay, but it's just to give you an idea what we do to try to interpret this deformation. I think well, you can continue play with this, but this is done for this practical, and then there is the lunch break.
Yes.
I will stop sharing.